Hi, everybody. Welcome to our first statistics lecture. This is our first introduction to statistics lecture, and it's going to be a gentle introduction to the course. We're not going to do too much math today. It's really going to be very basic and just giving you an introduction to some terminology and some concepts. We will really get into more of the concepts in the course later in the next lecture. So we're going to start with an example of a statistical study. So we're going to look at a study that involves administrating IV fluids. Nearly 25% of all emergency room patients are treated with IV fluids, intravenous fluids. And it's a way of giving hydration to a person who's in need of it. These fluids are typically stored at room temperature and infused into patients without prior warming. During infusion of room temperature IV fluids, some patients experience shivering, chills, and discomfort. So when the IV fluids are at room temperature, the patient's result is that they are somewhat uncomfortable. This is a true statistical study, and the link to it is here below, www.ncbi.nlm.nih.gov. This whole URL can take you to the details of this study. So in an effort to make sure that people are more comfortable, this study attempted to warm the IV fluids before giving them to patients. So warming the IV fluids to body temperature instead of room temperature prior to infusion may reduce shivering and improve patient comfort. So the idea is that we're trying to make patients more comfortable, but we don't have definitive proof that warming IV fluids can do this. So we go about trying to prove this with a statistical study. So warming IV fluids requires special warming equipment. It costs money, and it's not something that can be easily justified without good reason. So the process takes time. It requires training. Is there enough benefit to patients to invest in this process? So we ask ourselves, does the hospital have enough information that it needs to make a decision requiring it, or the decision to invest in this new process? So let's take a look at what happened. So what we're really doing in a statistical experiment like this one is testing for significance. Does the effect of warming IV fluids, is that effect significant enough to change ER hospital procedure? Because if it's only a mild improvement in comfort level, it may not warrant the cost needed to adopt this new process. But if the effect is more than mild, rather, maybe it's very significant, maybe it's a big improvement, well, maybe that is reason enough to change hospital procedure. So statistical experiments, also called statistical studies, can be conducted to determine how much patient discomfort is improved after being given warmed IV fluids. This particular experiment was conducted at an ER hospital in 2013. Okay, so let's look at the concept of samples and sample size. For this study, 27 patients were selected, and they were part of the experiment. We call these 27 people the sample. Okay, in all statistical experiments, the group of people that the experiment is conducted on is called the sample. The letter N, lowercase letter n, is the letter that we use to represent the sample when we do our statistical analyses. So here we write down that N equals 27. The number of people in the experiment is 27. And they fit certain criteria. They fit the criteria that require them to need IV fluids. They all had an acute illness preventing adequate oral hydration, required IV fluids, and they were between 18 and 45 years old. So these were the criteria for being part of this study, and all of these 27 people met that criteria. Okay, let's take a look at the terminology of a population. Samples are smaller groups of people or items that are taken out of populations. And the process of doing this is called sampling. The statistical experiment was conducted on a small sample, N is 27. All the people in the sample are part of the population of 18 to 45-year-old people requiring IV fluids. So this 27 are only the people that were part of the experiment, but, and if you look at this visual right here, the sample is a smaller piece of the entire population. In this case, the population would be every 18 to 45-year-old person that requires IV fluids. The experiment is conducted on the sample. So we are going to conduct our experiment on the 27 people that are part of the sample. But when we make conclusions out of our experiment, the conclusions that we make apply to the whole population. So if we're concluding that our 27 people received a significant improvement with warmed IV fluids, then we conclude that all people that require IV fluids between the ages of 18 and 45 would also have improved comfort levels. So a sample is part of a bigger population. Okay, so populations also have sizes, and they are much bigger than sample sizes. Population sizes are represented by the capital letter N. And the way you can distinguish that, or the way you can remember that, is sample is small, so it's lowercase n, and population is big, so it's uppercase N. Sometimes in a problem, we'll be given a value for capital N, the population size, and other times we won't. And that's because sometimes the population size is unknown. In the experiment about warming IV fluids, we don't know the population size, and often that is the case. So the purpose of sampling is to select a portion of the larger population and study that portion to gain information about the population. So we're doing this study so we can learn about everybody in the population who requires IV fluids. And we're trying to learn how the rest of the population would react under similar conditions. Data in a statistical experiment. The experimenters in the warming IV fluids experiment asked each of the study participants for a discomfort score. This was a scale of 0 to 10, with 0 being no discomfort and 10 being the highest discomfort possible. So imagine if you were part of this study, you were asked, what is your level of discomfort? And you give an answer from 0 to 10. They collected discomfort scores before and after administering IV fluids twice, one time with the warmed fluid and another time with room temperature fluid. The data that we collect from these patients are these scores, these discomfort scores, and we have data with all statistical experiments. This particular data is a discomfort score from 0 to 10. A different study, perhaps a study on blood pressure, would be collecting data of a different form. It would be collecting likely blood pressure measurements, or perhaps a different study on cholesterol would be collecting cholesterol levels. So data can take on different forms. In this particular experiment, the data is a discomfort level score from 0 to 10. Other studies are different data, have different data. Okay. The process of statistics as a whole, as a study, as an experiment, involves several parts. The first part is the collection of the data. Before we do anything with that data, we call it raw data. So imagine like raw food before you cook it. Raw data is data before you do anything useful with it. So in this picture up here, we have the raw data, and this is where the process begins. And you could see it like emptying into this funnel here. Out of the funnel, or rather inside of the funnel, we do a process, we do an analysis on the data. The analysis helps us interpret the data. We use various mathematical techniques in this analysis, and throughout the semester, that's what we're going to be doing. We're going to be using various mathematical techniques to analyze data. With that data, we interpret it and we present it in some kind of visual form, often using a visual like a graph. And then also coming out of there, we have an analysis and interpretation. So we can present our information, our data, and then we can look at what it means. And that's the analysis and interpretation part. So statistics, the study of statistics, is the collection, analysis, interpretation, and presentation of data. And what often comes first is the collection part. We collect the data first, and the other pieces, analysis, interpretation, and presentation, can often be in different orders. We may do a presentation before we do an analysis, but collection is the part that always comes first. Okay, so after collecting all the discomfort scores, that's considered the raw data, the experimenters analyze the data using statistical techniques. And those statistical techniques, we will see them this semester. They include a 5-number summary, confidence interval, and hypothesis test calculations. We are going to be looking at all of those. The experimenters interpreted the findings, and they found that treatment with warmed IV fluid was associated with a significant decrease in discomfort. So a decrease in discomfort, an improvement in how the patients felt. And the fact that it was significant is important here. So it wasn't just a little decrease, it was a big enough decrease to warrant it to be called significant. And in this class, we are going to define exactly what significant means. And we get to that a little bit later in the semester. Part of the presentation of their findings, the experimenters generated a graph to show the difference in discomfort levels with warmed versus unwarmed IV fluids. So I'm going to show you the graph here. I'm going to explain it a little bit, but we are going to get into greater detail with this type of graph in a future lecture. This is called a box and whisker plot, and I will be teaching it more thoroughly in a few lectures. The differences in discomfort from before and after the IV administration are plotted on these graphs. So what you see is two pieces. This part here is the use of body temperature IV fluid, which was a warmer temperature. And over here, what you see is room temperature IV fluid. And then on the vertical axis, you see discomfort scores. Actually, this is a change in discomfort scores. So these are differences. And 0 is in the center with meaning no difference. So this warrants a little bit of an explanation. So I'm going to share my iPad. And just bear with me a second. Okay, here we are. Okay, so imagine that we're part of this experiment together, and I'm going to see. My pen's not on. Okay. We're going to have two scores, one prior to getting the IV and one after getting the IV. So I'm going to put the before score here, and I'm going to put the after score here. And then I'm going to put the difference. And it's this difference that what got plotted in that box and whisker plot graph that you were looking at. So let's suppose that I'm in discomfort, and I'm at the ER, and I really am uncomfortable. So they give me a survey asking me how uncomfortable I am from 0 to 10. And I give my discomfort level at, I'm going to say 7. That was before they gave me the IV. And then they give me the IV, and I give a discomfort level this time of 4. So I'm not as uncomfortable. Now, the difference is what we get when we subtract the after number minus the before number. So we're going to take 4 minus 7, and that's going to give us a -3. So my discomfort level went down by 3 points. Now, let's suppose you did the same thing and you answered that before the IV, you were at a discomfort level of 6, and after you were at discomfort level of maybe 5. So not that bad. So we're going to do the same difference. We're going to take 5 minus 6 this time, and we're going to get a discomfort or a difference level of -1. So these two differences were then plotted along with all of the 27 other people. They were all plotted together. And let me go back to the presentation here. And that's what this score of 0 means. It's the difference between the before and the after. So with my discomfort difference of -3, that puts me like down here. Here's -2, here's -4, so -3, it's right around here. And your difference of -1 puts you right around here, okay? We're both below the dotted red line, which means that we both improved in our discomfort level. Whereas if we were above the red line, it would mean that there would be a difference in the other direction. We would not improve in our discomfort. We would actually be more uncomfortable after the IVs were given. So what we see happening here is that when body temperature IV fluid was administered, most of those 27 patients, you see how most of this graph is below the red line? Most of them had improved in their discomfort score, whereas with the room temperature IV fluid, most of the patients, most of the 27, you can see most of this graph is above the red line. Most of them were more uncomfortable after getting the room temperature IV fluid. So we see a big difference. And this is a visual representation of that difference. So let's keep going. So the negative difference, that's what you and I got with the -3 and the -1. That means our discomfort decreased. We felt better afterward. And a positive difference means our discomfort increased and we felt worse afterward. And that would be a positive or above 0 value. So looking at this, we can gather that the warmed body temperature IV fluid is mostly negative, mostly in the negative, while the unwarmed fluid is mostly in the positive. Okay. So when we take statistics and we organize it and summarize it in this way, this visual way here, it's called descriptive statistics. It's not only something that is visual, it could also be a single number as well. But this particular graph is an example of descriptive statistics. We will learn several types of graphs, and they're all examples of descriptive statistics, and that's mostly in the first half of the course. Finding the mean, the median, and the mode are also forms of descriptive statistics. Now, those are more numerical and less visual, but in the same way, we're using data with a single number to describe, we're summarizing data with a single number to describe the data. So we are describing the data, we're using descriptive statistics. Okay, most of the statistics you are probably aware of already in your life is descriptive statistics. This pie chart, for example, shows a split, a little bit more female than male in whatever this represents. This represents the proportion of ER patients who identify as female, 58.3, and this is a percentage. And males, 41.7. This is also a percentage. This is descriptive statistics to describe the makeup of the ER. If we calculate an average cholesterol level, that is the mean cholesterol level for a sample of middle-aged men, and we find that it's 210, that is also descriptive statistics. Like I said, most of the statistics that you may have come across in your life is probably descriptive statistics. If you calculate the median age for a population of mothers who deliver babies through cesarean section, and you find that the median age is 33, that's also descriptive statistics to find the median age of women in this population. So if all these things that you may have come across in your life are descriptive statistics, what is not descriptive statistics? Well, it's not necessarily what's not descriptive, but inferential statistics, what it does is it takes what you've already seen in descriptive statistics, but it takes it a step further. So inferential statistics, and after we learn several forms of descriptive statistics and how to calculate them, we are going to jump into inferential statistics. What we do is we use mathematical procedures to draw conclusions from the sample data. So oftentimes we will use descriptive statistics like the mean, the median, the mode as part of the process of inferential statistics, but it goes steps further. It takes it even further. Once we have those descriptive statistics, inferential statistics helps us gain a more useful understanding of our sample data. After we look at our descriptive statistics, inferential statistics will help us make conclusions and predictions about our sample data. It helps us make careful decisions. So similar to the way the hospital in the ER in that hospital would choose whether or not to invest in warming the IV fluids, that's an example of using inferential statistics because they made a conclusion based on the data, based on the descriptive statistics. They made a conclusion that the improvement was significant. And when we get to that point of inferential statistics, we will learn about what significance truly means and how we can make similar predictions and similar conclusions, and therefore guide our decisions. So here it is side by side, descriptive statistics. We are creating reports and graphs that provide information or describes or summarizes the data. Inferential statistics, we collect data from a sample and we draw conclusions about the population from the sample. So we go further with inferential statistics than with descriptive statistics. Descriptive statistics you could probably do in a class period. Inferential statistics would take you a little bit more time if you were doing it in the real world. Okay, here's an example. The mean age of a first-time mother, or I'm sorry, the mean age of first-time mothers in the US in 2021 was around 27.3 years old. That's descriptive statistics. It is a mean and it represents a piece of data. It's the age of first-time mothers in the United States. Okay, now we have another example of descriptive statistics. We have a sample mean of first-time mothers in a county in New York, specifically a county in New York, and a sample out of that county, and they found that the age was 30.1 years old. That is also an example of descriptive statistics. But what inferential statistics would enable us to do is to take those two descriptive statistics and decide if there's a significant difference between them, between 27.3 and 30.1. Is the difference significant enough for a hospital to perhaps change its process in the maternity department? So if we apply inferential statistics, and the process is called a hypothesis test, and we're going to learn about that later on, we can make educated conclusions about the sample data. Hospitals in the New York County can use these conclusions to make decisions regarding prenatal care and delivery procedures. So while descriptive statistics gives us the quick data, inferential statistics guides our decision making. Okay, statistics from samples. So let's look at this pie chart again. Sample of patients in a hospital emergency room, 58.3% versus 41.7%. So the term statistics has a broad meaning as a branch of mathematics that deals with the collection, analysis, interpretation, and presentation of data. And that's the course you're taking, statistics. But it also has a second meaning, and it's a smaller, more precise meaning that's used when to describe something about a sample. So the single used in the singular, a statistic, is a number that's used to describe a characteristic of a sample. So yes, we have the broad terminology, the broad term statistics to represent the entire branch of mathematics and this course as a whole, but we also have this single number. A statistic is a number to use to describe the characteristic of a sample. So here, in this sample of patients in a hospital emergency room, 58.3 is a statistic. It represents the females, and 41.7 is a statistic that represents the males. And here's another example of a statistic. In the IV warming fluids experiment, remember that the sample was those 27 patients. We weren't working with the entire population. We were working with a smaller sample of 27 patients. And the people who conducted the experiment discovered that the average here, or I'm sorry, the median change in discomfort for the 27 participants in the sample was negative 0.7. And that negative 0.7 is a statistic because it describes a detail about that sample of 27 people. Okay, it's a single number that describes a characteristic about a sample. Here's some other examples. This is from a study. I'm looking at a pie chart that's from a study after post-COVID-19 conducted in North Carolina. It was called the Vision Study. And you can see that 11 or 1,183 people N equals 1,183 down here. Data collection began in January 2023, and it's a study about long COVID, people who exhibit symptoms of COVID after having contracted it months and months later. Okay, so what we're looking at here are the data from the sample. We're looking at people who experienced no long COVID, that's the pink, 88%. And we're looking at people who, I'm sorry, no long COVID is the 88%, and blue, long COVID is the 12%. So we're looking at these two numbers, these two proportions, they represent the sample from this n equal 1,183. So it's a sample. 1,183 is a sample. It is not a population because, of course, we know many more people had COVID, and in particular in North Carolina, where this study was conducted, many more people than those 1,183 had COVID. So these numbers, 12% and 88%, are considered to be statistics because they represent that sample. They are not representing the entire population, they represent that sample. Okay, so they are statistics. Now let's take a look at what the opposite of a statistic would be. A statistic is a number that represents something about a sample, but a parameter is a number that represents something about a population. So that is the opposite of a statistic, parameter. Oftentimes, we don't have parameters and we use statistics in their place because statistics from samples are much more easy to come by than access to an entire population. Now, population data is very hard to get because the populations are often very large. That's why we conduct a US census every 10 years because they are not easy and quick and cheap to do. They take a lot of time and effort. So, but when we do have the data from a population, we can extract a parameter from it. A parameter is available if we examine data from a census. Okay, and a census is what we get when we look at the whole population. So, for example, census data in the US from 2020 shows that 16.8% of the population were aged 65 and older. Census data from 2010 shows 13% of the population were aged 65 and older. So, two different decades, 2020 census and the 2010 census, and 16.8% from the 2020 census and 13% from the 2010 census are both called parameters. They represent the whole population. Okay, so a statistic represents a single number or is a single number that represents a sample, and a parameter is a single number that represents a population. Here's an example. A team of doctors is interested in determining the proportion of patients who get bacterial infections post-abdominal surgery. The doctors select 440 patients who have undergone abdominal surgery. And let's remember that 440 patients were part of this study. And they determined the proportion of bacterial infections is 18.9% in those 440 patients. We are asked here, what is the population? What is the sample? What is the parameter? And what is the statistic? Now, in some of those answers, we'll be able to give an actual number, and sometimes we don't know the number because it's not provided in the question. But even if it doesn't provide the number, we can define what each of these things mean. So first, the population. The population, remember, is everybody. If this study is conducted on people who get bacterial infections post-abdominal surgery, then the population is all the patients who have undergone abdominal surgery at this hospital, all of them. And remember, the sample is that smaller subset. So the sample is just those 440 selected patients who have undergone abdominal surgery at that hospital. So that smaller portion of the population. And we were not given the size of the population in this problem, but we know we can define what it is. It would be everybody who got abdominal surgery. The parameter is the number that represents the population. Now, again, we don't have it here. It is but we can define what it means. It's the proportion of patients with bacterial infections after abdominal surgery in the population. We don't know the size of the population and we don't know the proportion of patients. So in this problem, the parameter is unknown. But that's what it represents. It would be the proportion of patients in the population with bacterial infections after surgery. On the other hand, what we do know is the statistic. The statistic is the same thing, but it represents the sample. The proportion of patients with bacterial infections after abdominal surgery in the sample, and that is 18.9% as given to us by this problem. So, population, all the patients who fit the category, in this case abdominal surgery. Sample, the selection of patients that were part of the study, 440. Parameter, the proportion of bacterial infections from the population. And statistic, the proportion of bacterial infections from the sample. And it is provided 18.9%. And this was an actual study, so the link to that is down here below if you want to click that. From the presentation, you can click that and read more about it. Okay, sampling. When conducting statistical analyses on samples, the samples must be representative of the population from which they are taken. Why is this important? So the word representative means that it should reflect the population from which it's taken. The sample should reflect the population from which it's taken. A representative sample has similar characteristics of the population in similar proportions. Take a look at this sample. Oh, no, I'm sorry. This is a population. It says at the top, all ED visits, emergency department visits, and we see a capital N, so we know we're dealing with the population. And we are given a huge number, 141 million and more, okay, visits to the ER. In this population, we have various parameters, okay? 54.9% were white, 15.4 were Hispanic, 20.7 were Black. Over here, Asian Pacific Islander, 2.1%, and other, 4.1%. These parameters represent the population. Okay, and this is an actual study as well. Here's the link to that if you want to take a look. These are all ER patients in the US in 2019 by ethnicity. Okay. Now, let's suppose, now that's real. This N here is real and these parameters are real. But let's suppose from that population, we sampled a smaller group. This N equal 1,000 is the smaller group that we sampled out of the population. And let's suppose that we grabbed these proportions. I'm starting with white again. White 19.9, just 19%. Okay. This is a statistic because it's representative from the sample, or rather, it's a characteristic of the sample. Hispanic, 20%. Black, 10%. Asian Pacific Islander, 50%. Other, 1%. Suppose we gathered that sample for a study on ER procedures, and our sample contained those proportions. What's the problem here? Well, you should recognize that the problem is that the proportions are way rather disproportionate. Take a look at the difference between, I think the biggest difference is the smallest percentage in the population, Asian Pacific Islander with 2.1% here, became the biggest proportion of the sample with 50% here. This is not a representative sample. It does not represent the population. And this is not good. This would make for a poor study if we used a sample that looked like this. So here it is again, that bad sample, a non-representative sample. Our sample does not have similar characteristics of the population in similar proportions, so we call it a non-representative sample. It's also called a biased sample. If we were to use this biased sample in a study, and if we were to make conclusions from it, our conclusions would not be trusted. Okay, our representative sample or the non-representative sample would produce a flawed study, and the conclusions would not be trusted. So we want to reduce this chance of creating a bad sample, of having a study that can't be trusted. And we do that through randomization. If we make our sample through randomization, it helps our population, it helps ensure all the groups in the population have proportionate representation in the sample. So if we use random techniques to create our sample, we're going to naturally discover that the biggest proportion would be white, the smallest proportion would be Asian Pacific Islander. If we used true randomization, we would not get this biased sample that we see on the left. We would get something that looked more like this. Maybe not exactly like the population, but it would be close, okay? We wouldn't see drastically different proportions. Okay, and how do we do that? Oftentimes randomization can be done in a simple method. If you think about pulling lotto numbers out of a lotto machine like this, it could be done easily like this. We want to make sure that each member of the population has an equal chance of being selected. It would make sure that our sample is not biased. And we do this by taking these randomly selecting items out of the population. That produces a simple random sample. So we randomly choose members of the population to be part of the sample. To be truly random, imagine if you put all the names of a population in a hat and you blindly choose a selection to be part of a sample. That's something that was done like when you were in school as a kid. And then in lotto games or bingo games, it's being done in like a machine like this, where you rotate it and out come the numbers. Supposedly every one of these in here is unbiased. They're all the same and they have the same equal shot of coming out and being selected. Technically, oftentimes you would use something in maybe some kind of spreadsheet, a random number generation that would enable you to randomly select numbers. And it makes that's a more practical approach than to put numbers in a hat and draw them out, especially when you're dealing with large populations. And if you wanted to create a sample of size 1,000, like the example was before, 1,000 is a lot of numbers to put through a bingo machine like this, so it's more likely that random number generation would be done on a computer or some kind of program. Okay, so here's an example of an easy small population that's being randomly sampled to create a small sample. So the population you see here, these are supposed to be people, and they're numbered 1 through 12. And these people, randomly selected people, have different characteristics. We have blue people, we have red people, and we have green people. And it looks like we have more red people than anything else. And we have 3 green and 3 blue. And on a larger scale, if we had a population like this, a biased sample would have more of one color that, instead of the larger proportion being red, maybe we'd have a large proportion being blue. But if we use randomization, we should have the largest portion being red in our sample and the smaller portions being green and blue. And what you see here is exactly that. From from this population, we randomly select a 2, the 5, the 8, and the 10, and our smaller sample of size 4 here has got 2 red, a blue, and a green. Okay. So the population is on the left. Every member is assigned a number. A random number generator is used and generates the numbers 2, 5, 8, and 10, and they become part of the sample. And I do want to show you how, and this is actually a little, I wanted to show you how you can use your calculator to do random number generation. And this is actually not something we're going to be doing too much of this semester, but it's an interesting feature on your calculator if you wanted to try it out and just get an idea of some of the things that your calculator is capable of. So you get started by clicking Math, and then using these arrow keys, you're going to slide over to the Prob for probability menu, and then down to number 8, rand int no rep, and that stands for random integer no replacement. When you choose that, you're going to be brought to another screen where you give a range of numbers that you want to generate. We're going to generate numbers between the range of 1 and 12, and the number of numbers you want to generate, and that's the sample size n. The no repeat, or I'm sorry, no replace means that from your 12 numbers, when you select one, the calculator is not going to replace it back in the set of 12 to be chosen again. Once it's chosen, it's out and it cannot be chosen again. It will be part of your sample and it can't be reselected. So that's ideal for doing things where you're selecting people to be part of a sample because there's not more than one of a person. You select one and that's it. So we want to use the no rep in this case for no replace, and these are the criteria: 1, 12, 4, and then we go down to paste and hit enter. This brings us to our home screen, and then if we hit enter again, we generate the 4 random numbers, and notice that they're not in an increasing order from left to right. They're truly random, and none of them are repeated. So 4, 3, 12, and 1. If I want to repeat this particular function on my calculator, I can do second enter. That just repeats the previous function that you just entered on your calculator. So whatever it was, it could have been an addition problem. It would just repeat that last thing. So if I repeat it, I should get a different set, and I do, a different set of 4 numbers. And I do it again, I should get a different set of 4 numbers, although I seem to keep getting that 12, which is interesting. It should not, yes, that's just coincidence, so it is just coincidence. If you wanted to repeat this on a larger scale, hit the math button, prob, go down to rand int no rep, and maybe you want to do it between the numbers of 1 and 99, and maybe you want to pick 7 numbers out of that range. And this would generate 7 random numbers. So this is one of the things that your calculator is capable of. It's a fun thing to do if you are playing a game. So you can give it a try if you're interested. And I just wanted to introduce you to that and use it if you like. Okay, so on a large scale, random number generation would probably be done with spreadsheets or some other kind of computer program. And what's going to happen on a very large scale is your population would end up yielding a sample that is non-biased and representative. members of the population will be represented in similar proportions in the sample as well. So you wouldn't have one group disproportionately represented in the sample. Everything would be equal in similar amounts in the sample. Okay, so we're pretty much done with the intro stuff. I'm going to get into some misuses of statistics, and that's going to conclude the lecture. So the first thing I'm going to talk about is a true example of a biased sample that occurred earlier in the 1900s. Statistics really has evolved, and it's a very modern branch of mathematics. Statistics is something that really came into being and statistical studies in medicine, for example, were really perfected in the last century. So there were some learning curves along the way, and one of them is this experiment that was done in 1930. It was in Lanarkshire in Scotland, and it was conducted on school children in this town or city. And the goal of the experiment was to see if milk improved growth in children. And it seems like it could be a very valid experiment to be conducted in different groups to see if milk was beneficial. So they started with 10,000 students, and they were given 3/4 of a pint of milk per day in school. Um, that was considered to be the treatment group, and 10,000 students were not given milk, and that was the control group. And they were weighed and measured before and after a 6-month period. So this has the makings of a really valid statistical experiment. But the problem arises when you look at how the samples were selected. And this, unfortunately, made this study invalid. The children were divided into the control and treatment groups at their schools alphabetically by name, by their last names. But after they were in their groups, teachers made substitutions. So after they were randomly selected or put in through their last name, which is supposedly a non-biased approach, the teachers would hand pick and change the groups. So the teachers would say, oh, well, this group looks to be imbalanced. It looks like there's too many malnourished children in this group. So I'm going to try to balance it. And the teachers would manually change the children in the control and treatment groups. So if it appeared that there were too many malnourished children or well-fed children in a particular group, the teachers would manually make these substitutions. And so what happened is the teachers overcompensated. They substituted too much, and the groups were disproportionate. There were more malnourished children in the treatment groups, and those are the students, the kids who got milk. They were all smaller and lighter to begin with. And there were more well-fed children in the control group. They were taller and heavier to begin with. The samples were biased, and the experiment, therefore, was spoiled. Like the milk, it was spoiled and not trusted. And I'm putting the picture here of the famous statistician who discovered the problem with this experiment, W.S. Gossett. He publicized the experiment's failures in 1931, and he is the founder of a lot of the statistics that we will learn later on in the semester. Okay, here's another example of misleading statistics. It may be a little hard to read this graph, but this is a recent application of a misuse of statistics. It was COVID-19 cases. The chart below represents the most impacted counties over the past 15 days and the number of cases over time. The table below also represents the number of deaths and hospitalizations in each of those impacted counties. These were counties in Georgia in 2020, spring of 2020. Let's look at the trend from left to right. The different colors are the different counties. You could see Cobb, DeKalb, Fulton, Gwinnett, and Hall counties. Okay, and what we see from left to right, we look at this trend that appears as if these bars in generally are moving down from left to right. Look, and the last one is really low. Like the first is really high, and then they go downward, and the last is really low. But if you look a little bit more closely, the horizontal axis is not chronological. It has dates, but the dates are not in order. So what you see here is the 28th of April, 27th of April. Then you see the 29th of April, May 1st. Then you see April 30th. Then you see May 4th, May 6th, May 5th, May 2nd. So this is not going in a chronological order at all. What we would expect is that you start with the earliest dates at the far left and it increased to the later dates on the far right, with the very last one being the last date. And in fact, it happens to be May 9th. That is the last date. But there's a bunch of messed up dates in between, and things are not in chronological order. That's the misuse here. And this is, you can actually click this link to read about that mistake. The highest number of cases are clustered on the left. That's the way it's made to appear. And the lowest are on the right. That's how the person who made the graph wanted it to appear. But if you look at close inspection of that x-axis, that horizontal axis, it's not chronological. And that is a misuse of statistics. The graph appears to show a consistent decline. Okay, a consistent decline in the number of cases in all 5 counties. But when you place it in chronological order, it is not the case. Now, unfortunately, I could not get a graph that was in chronological order because I'm pretty sure that once the people who made this were called out on the mistake, they decided to not publish the true graph because it would not demonstrate the numbers in the way that they wanted it to be shown. So that's probably why I can't find it. But you could imagine that it would start off and then it would go down and then it would go up and down and up and down. And there'd be a lot of increase and decrease instead of this steady, seemingly steady look of decreasing all the way. Okay, and so mislabeling graphs is an example. And the last example I'm going to talk about is this sociologist, misrepresentation and fraud. This sociologist, or I'm sorry, he's a social psychologist, Diederik Stapel, uh, in the Netherlands, I believe. He was published in some of the world's top journals, including Journal of Experimental Social Psychology, Basic and Applied Social Psychology, British Journal of Social Psychology, and the magazine Science. Very highly regarded man in his field. But what it was shown is that he really faked a lot of the data that he presented to the public in his research. An investigation involving 3 universities where Staple has worked concluded that the psychologist is guilty of fraud on a colossal scale. He falsified data, I don't know what that, I think I have a misspelling here. Over 55 papers, he falsified, I think this is supposed to say data sets. In over 55 papers he authored and 10 PhD dissertations that he supervised. This link takes us to the OpenStax textbook that talks a little bit about the problem, but there's more I can share with you. He was found guilty of several practices, including creating data sets, which largely confirmed prior expectations. So imagine that I conduct a medical study like the warming IV fluids study, and instead of truly getting those numbers from patients, I made them up. Okay, that's what creating a data set is, making up the data yourself and making it in a way that's confirming a prior expectation. So creating data to promote a particular point of view. Altering data in existing data sets. So maybe you have a data set, but it didn't look the way you wanted it to look. So you fudge the numbers a little bit. changing measuring instruments without reporting the change. So how are you going to take people's the discomfort level? How are you going to retrieve those values from people? That's a measuring instrument, without reporting the change. And then misrepresenting the number of experimental subjects. So perhaps the number of people he was working with, and perhaps he inflated the number. There's a nice article in the New York Times about him. So if you want to read more about that, this was from 2013. You can click in the presentation and you can go to that article, if you're interested. So that's an example of a misuse of statistics. And you could imagine there are hundreds of examples of bad graphs, bad people, and what was the first thing that we talked about? And just bad studies that have bias in their samples. There's lots of examples of that. And your job is to be educated enough that when you come across something, approach it with skepticism, approach it with a critical eye, and make sure that all the pieces of the experiment seem to be valid and trustworthy. Okay. Vigilance against fraud requires knowledge, and that's what I hope to give you this semester. Learning the basic theory of statistics will empower you to analyze statistical studies critically. Okay. So what's coming next? Well, first, a recap of what we did. Important terminology. What is a sample? What is a population? What are statistics and what are parameters? And what's a simple random sample? So we discussed all these things today. I talked about some ways in which statistics can be misused. Thinking critically about data will help you collectively recognize these misuses and address them. Okay, what we're doing next is we're going to start getting into some topics where we're actually going to build some descriptive statistics ourselves. We're going to create and calculate descriptive statistics beginning with the stem and leaf graph. That is what we're going to be doing in our next lecture. So I hope this introduction was helpful and not too scary. And I look forward to talking with you at the next lecture. Have a good week, and I'll see you next time.